and we showed how you can use this for passing by reference, right? We had that swap demonstration where the first version didn't work because we were passing by value. 10 and 20 copies of 10 and 20 were handed off to that function, and the copies were swapped. The original variables were not. But once we've changed it so that it used pointers, those pointers pointed back to the original variables so that you could actually swap those original variables, right? And now what we're going to do is we're going to continue to use pointers to pass by reference in more applications. That demonstration was just to show you the usage of pointers. That's not actual code that you would ever probably want to write. If you just want to swap two variables, you just do it with 3 lines of code and that's it. So when does passing by reference actually become useful? Well, you've seen one use case already, right? Remember scanf. Scanf, what did you have to do with your variable? What symbol did you have to put in front of your variable? The ampersand. Why? Because you were passing it by reference, right? So I'm scanf now, right? I'm going to go ahead and read the keyboard masher's input. They typed in 1, 2, 3, right? I'm going to take 1, 2, 3. What do I do with it? If I put it into a variable x that has been passed by value, right? Just like that swap demo, it dies with me, right? When the stack frame gets popped off the top, this 1, 2, 3 is lost. But if you gave me a pointer variable, then I can jump to that memory location and put 1, 2, 3 in that memory location. And that's why scanf uses pass by reference. Values. So does that sound like a function? Remember, what is a function? A function in math, a function is just like a function in math. Can math functions return multiple values? Nope, that would fail the vertical line test. The circle, right? That one x value maps to 2 values, right? You can't do that. That's not a function. That is something mathematical called a relation that you'll eventually see in, say, 235, but that's not a function. A function is a very special type of relation, but you can't return multiple values. But here, we can return multiple values. How? Let's go ahead and design, and I'll go ahead and zoom in on this. It all looks good. Oh, I never checked the audio. Yeah, it's working good. All right. Oh, 2 people are online to check it, so let me know if there's any problems. Again, if you're online or if you're in here watching the live stream along with it, there is a 10-second delay. But if you have any questions, you can post to the live stream and I'll see it. Anyway, let's go ahead and create create a function to compute statistics on a circle. Right? So for example, given the radius, I want to compute the area and the circumference. I want to compute 2 things about this circle. Now, as you saw in your lab yesterday, if you want to compute multiple things, you need another function. You need another function, right? If you want to compute RGB values of a sepia image, you need the red value, the green value, the blue value. That means that you had to write 3 functions, right? But now with pass by value or with pass by reference, we can write 1 function, right, with 3 variables that are passed by reference, and then assign each one of those variables a value, right? So what I mean by that is, if you just wanted to compute the area, that's 1 function. If you wanted to compute the circumference, that's a 2nd function. I'm going to write 1 function to do both of them at the same time, okay? So let's go ahead and call this function compute circle statistics. There we go. And I'll go ahead and put the let's do it correctly. Let's do the prototype up here, and then we'll go ahead and define it down here. Right? And we're going to have to come back and forth. So if I'm going to compute both of these things as pass by reference values, I don't have any return type anymore, void. We're not going to return the area. We're not going to return the circumference, because if I returned one or the other, I wouldn't be able to do anything with the other one, right? So what I'm going to do is I'm going to take in as input here a radius, but also a area and a circumference, right? But that are passed by reference, pointers, so that I have these 2 buckets that I can fill with 2 values. Right? You give me these two buckets, right? You have references to these two buckets. I can jump to those memory locations and fill both of those values, thus returning, and again, it's double quotes here because I'm actually not returning anything, am I? It's a void function. So I'm effectively returning two values here. What does this look like? Well, given the radius, right, what's the area? Pi, m sub pi, r squared, so that's radius times radius. Right? That's the way I would do it. First of all, don't use your own definition of pi. It's in the math library, use it. And if it's in the math library, what do I need to do? Include it. Right? Several questions, and not in this section, but several questions on the other Piazza sections the other day of, it won't compile because you're using math and you haven't included the math library, right? So the first 4 weeks were thrown out, right? Anyway, don't use your own definition of the math of pi. I've got radius and radius, right? Another way of doing that would be pow radius raised to the 2, right? And you can do that, but your compiler is probably going to optimize that away. Why? Because one multiplication is simpler and more efficient than some whatever interpolation method is being used for x raised to the power y. It would actually replace your code with this code right here. So you might as well just write it like this. Right? There's the radius, or sorry, not radius, area. Right? There we go. Is that correct though? The thing on the left-hand side, is that a regular old variable? The thing on the right-hand side, that's a regular old value, right? Pi r squared of a unit circle is going to be 3.14159, whatever. But the thing on the left-hand side, is that a regular variable that I can assign a value to? Nope. So, review. Again, where's my summary? Oh no. Okay, there we go. There it is. A regular variable can be changed into a pointer variable using the ampersand, just like scanf. A pointer variable can be changed into a regular old variable so you can assign its value or retrieve its value using the star operator. So what do I need to do in this case? I've got a pointer variable, right? Double star. And what do I need to do to it? Dereference it so that I can set its value equal to pi r squared. Likewise, what about circumference? Circumference, there we go. What's the equation for circumference? Oh, we don't remember that? The circumference is the distance around the edge of the circle. Oh, don't you remember pi r squared, but not pi d? Right. Pi r. Yeah, there you go. 2 times pi r radius. There we go. Right. Or pi d. D is the diameter. Diameter is twice the radius. Right. There we go. And that's all I need to do. Right. Instead of writing 2 functions, I can say I want multiple values. Now next week you'll do the same thing with that image manipulation program that the filtering program that you're writing, right? Instead of writing 3 functions for red, green, and blue, you will incorporate those all into one function. Likewise for the grayscale. Instead of having one for one mode, another for another mode, another for another mode, you're going to collapse those all into one function that takes care of all of it. Right? We'll see how by the end of the week here. And then, of course, you'll do it next week. So how would I end up using this? Double radius. Give me your favorite radius. What? Yeah, a 4? Okay. I was thinking, do something that's easy. Right? Do something that you know the answer to immediately out of the gate without having to pull out your calculator. 1? Why 1? What will the area end up being of the unit circle? Oh no? Pi, right? And we all know pi, right? And what about the 2 pi? Of course, that's going to be easy. Just double up whatever the first answer you get. Okay. All right. So let's go ahead and call this function. Compute circle statistics given the radius, and what about these other 2 things? I need variables for them. So it expects a pointer here, right? So let's go ahead and create a pointer. Double area, double star area, that's a pointer. And I need to initial, I'll leave it like this for now. Right? And I don't like typing that out, so cut, paste. There we go. Now, I could pass those. In fact, I could go ahead and really drive home the point that these are different variables than these variables over here, right? But then those would be bad variable names, right? So I'm going to go ahead and keep it like that. Area and circumference, comma. Is that going to work? As of line 14, area and circumference are pointers, right? What are they pointing to? If I didn't have a radius initialization here, what value is stored in radius? In radius, a radius is not a pointer. Radius is a regular old variable, so it could be 0. Likely it's going to be 0. It could be garbage. It could be dead beef, right? It could be anything. An uninitialized variable does not have a default value. That's why we initialize our variables. What did we initialize pointers to if we didn't know where to point them to? Null, right? Now, is this going to work? Okay, now we know what they're pointing to. They're pointing to nothing, right? They're pointing to, now they're literally pointing to, actually it's less than garbage, right? Garbage is at least something. This is nothing. Am I going to be able to dereference it? Nothing in order to put into it the value 3.14159? Let's find out. Where am I? All right. Lecture CSE 155H. There we go. GCC demo.c. Uh-oh, what should I have done probably? Hopefully the wall flag here will notify me that I probably have, oh, nope, it doesn't, unfortunately. But what's going to happen here? Well, let's actually print this stuff out. Printf the area and circumference radius equals %f. Yeah, I'm keeping working. Right. R %f and %f. And the line, so this is going to be radius, area, and circumference. I want to make sure that the compiler doesn't compile everything away because you're not actually using any of those variables. Right? There we go. Oh, yep. Okay, so it is complaining about things already. I dereference those. We'll come back to that. Okay? There we go. So predict what's going to happen here. We've got area that points to nothing. We pass that pointer off to compute circle statistics, which then tries to dereference the nothing pointer. Is that, if I'm not pointing to a bucket, is there a bucket to fill over there? If I'm just pointing to the ground and I go to put whatever I'm pouring into the bucket, what's going to happen? I'm just going to pour it on the ground. It's not going to go into the bucket. So what's going to happen here? A segmentation fault. Right? I tried to dereference a null pointer, right? An invalid pointer. And when I do that, it sees, you're trying to illegally access memory that doesn't belong to you, a segment of memory that doesn't belong to you. That's a fault. We're not going to let you do that. We kill the program. Again, imagine if you could do this. If you could access memory that doesn't belong to you, that means that you could access like sensitive information, passwords that are being stored in memory in another program, SSL keys, cryptographic keys, stuff like that. Right? So this is not the way to do it. Let's create regular old variables, double area and double circumference. Right? There we go. Then we don't have to dereference them here. There. So now I am assured that they actually exist in memory, right? These are two regular variables which we've been using for the first 5 weeks here, right? They exist, right? There's not going to be a problem here. But when I go to compile this, it's going to warn me, right? Wait a second. This is incompatible. You said that you wanted a pointer to a double, but you're giving me a regular old variable. So once again, how do I take a regular old variable and change it to a pointer so that you get the memory address of that instead? I use the ampersand, just like scanf. Okay? Now it is a valid variable that it can reference and dereference all you want, and it'll actually work. That second one is definitely pi doubled up, right? Okay. So there's one use case, right? With pass by reference, you can return multiple values now, right? Now you don't need an entire collection of functions to compute multiple values and then use them independently. You can go ahead and collapse that down to one function, okay? Another nice thing is, even if you only have one result, it still is a good, still might be a good idea to use pass by reference. ... Let's go back to an example that we were working with before. AGM, okay? Remember, AGM is the arithmetic geometric mean. We take two values, right? And then we compute their arithmetic mean, which is just x plus y divided by 2. Their geometric mean, multiply them together, take the square root, right? And then you do this over and over again until they converge onto some number. Not my math test, but this one. There we go. Right? So we've got this while loop. While these two values are far apart, right, then we go ahead and continue until they converge on each other. Okay? Now, one thing that I didn't mention before was that this is not defined for negative values. X and Y both have to be positive. By the way, if one of them is 0, that's okay to define it that way, but then what's the arithmetic geometric mean? It's going to end up being 0, right? Because the square root, the product is going to be 0, the square root of 0 is 0, and you'll never get anywhere. And then the other one will eventually converge on 0. But we'll only accept, in this case, positive numbers, right? So I'm going to put that into my documentation here. The input values must be positive, right? As AGM is not defined for negative or 0 values. Okay. Is there a way of handling that case? What if somebody did give me negative values in this function? What should I do? If x is less than or equal to 0, or if y is less than or equal to 0, what do I do? Printf. Here's the bad way of doing it, right? And then we'll improve on this later. You cannot call this function on negative values. All right, well, maybe that stops the whole show. Exit 1. There we go. We killed the entire program because you gave me a negative value. All right? Now, does that sound like a good idea? Probably not. Let's take, initially, let's just take a cue from the standard math library. If you called square root on a negative value, does it kill your entire program? No, it just results in not a number. And then you can choose to handle that. Like, if it's a negative number, okay, I'll go ahead and do something else, right? Or I'll move on because it's not that big of a deal, right? I'll choose how to handle it. If square root did exit the entire program, right, then that's far less flexible, because that means that it's making a choice for me, and I have no choice on how to handle that situation, right? Likewise, does square root say anything about it? Does it print out to the standard output? Nope. Why not? Because the vast majority of software is not written for humans. Right? The vast majority of software is for software to communicate to other software. It's called glue code. If you've got one system and another system, and they're in different technologies, different languages or whatever, or different servers, you need to communicate back and forth. That's where the vast majority of software is actually written. Why do we write software to begin with? To automate stuff. Right? It's not automatable if you have to sit there and stare at the computer waiting for something to happen. And something happened with a negative value. Now I need to start working, right? No, you write programs so that you can start these tasks and they're all automated, right? That gets into error handling, which is what we're going to start discussing next, okay? But I'll leave this in here for now. We're going to look at a better solution. So, to do, fix this bad solution, okay? But what I want to do right now is I want to change this so that it is returning its value as passed by reference instead. So double result. Right? And I'm no longer going to return the value. Instead, I'm going to return the value using this pass by reference variable here. How does the function change? I don't return anything anymore, do I? Instead, at the very end, what do? Result is equal to current A. Is that correct? Careful. What's the thing on the left-hand side? Pointer. What's the thing on the right-hand side? Not a pointer. So what do we need to do? Make the thing on the left-hand side into a pointer, or into a regular old variable, right? And again, this is just your sticky note that you're putting above your desk from now on until you get it in your head. A pointer variable can be changed to a regular old variable using the star operator. Star. There. And now, of course, I do also need to change the prototype here. Oops. There. To match. And in your math test, of course, you'd have to change everything so that it's passing by reference instead. I won't go that far, though. So, why did I go through that exercise? Right? Why did I say, oh, even if you only have one result, maybe it's a good idea to pass it by reference in order to free up the return value. Right? This is where we're going to fix this bad solution here. Right? I want to know if something went wrong. So let me go back over to this demo here, and we're no longer doing circle statistics. Instead, we're doing AGMs, right? So double x is equal to 42, double y is equal to negative 42. What's the AGM of x and y? Undefined, right? Include my math library here, mymath.h. Right? So if I were to call this AGM on x, y, and result, I need another double here for result. And pass it by reference. There we go. And then I can print it out. Printf. AGM of %f is equal to %f and the line. There we go. If I call this function, what's going to happen? Let's go into that function now. It's going to quit on me, isn't it? Let's go ahead and try it. So GCC compile mymath.c, right? Okay. So if you're going to do standard stuff, include stdlib.h. There we go. That's where it is. And then I'm doing output stuff, include stdio.h. There we go. Fine. Now everything is included. GCC, oops, come on. mymath.o, and what was it, demo.c? There we go. Oops, what's wrong? So it's a double those are all double arguments, weren't they? X, Y. Oh, I didn't put them there. X, Y, result, right? Did anybody see that error? Okay, go ahead and yell at me if you see it before I have to have the indignity of having the compiler tell me about my errors instead. Right? All right, so let's run this. Again, what's going to happen here? I give it a negative value, and the design of this function has decided that if you give me a negative value, I'm just simply going to quit on you. Right? You cannot call this function. And I'm going to also give you the error message here. You can't call this function on negative values. Right? It's kind of rude, right? It's inflexible. Right? What if I wanted to do other stuff after that? Right? And I wanted to say, well, okay, fine. Negative value, that doesn't work. I'll try something else. Right? I'll do something else. I'll reprompt the user for better input. I will output to a log message saying that somehow we got a negative value from this. You need to check this out. I'll shoot off an email to the system automated email that says you need to take care of this situation. Right? That decision-making process was taken from me with this. Right? I'm just going to quit on you. Right? So let's take out that bad solution here. Instead, what I want is a solution that says, here's your input, and now I'm AGM, right? Now I'm from the the function's perspective. Okay, I can't do anything with this, right? I'm not going to quit. I'm not going to give you any rude messages that you can't do what you're doing. Instead, what I'm going to do is I'm going to go back to you and say, an error occurred, right? The only way that I can do that is by giving you a return value, right? An integer. Right? If this does in fact happen, what I'm going to do is I'm going to return a value here. Return, and for now I'm just going to return 1. Right? Otherwise, if there is no error, what I'm going to return is a 0. Now, the reason I'm using 0 and 1 is because it's consistent with everything else in C. What is false in C? Do you remember? 0. What is true in C? 1. What else is true in C, though? 2, 3, anything that's non-zero. Right? So what I'm going to do is I'm going to split this apart. Right? I'm going to split this apart into 2 conditions. That if you give me a bad number for x, that's an error of type 1. Else if you give me a bad value for y, oops, there we go, that's an error of type 2. Right? And if there was no error, then I'll return false. You're asking the question, was there an error or not? False, there was no error, 0. True, there was an error of type 1. True, there was an error of type 2. And if you have any other values that you, or any other error conditions here that you want to enumerate and say, well, this is an error condition, this is an error condition, this is an error condition, you can go ahead and continue because you're not running out of numbers anytime soon here. What's another error condition that we saw before with a pointer? What caused the seg fault? Null. Else if result is null, then I'm definitely not going to touch it, because if I dereference it down here on line 32, it's going to result in a segmentation fault. That's a different type of error. That's an error of type 3. Right? So however many error conditions you have, you can communicate that back to the calling function using the return type, which is only possible because now we're returning the actual value, the actual result, in a pass-by-reference variable. Right? We've saved the return value here for an error code. These are error codes. You've seen this before, right? Exit 1, you're exiting with an error code of type 1. Exit 2, you're exiting with an error code of type 2. Exit 0, you're exiting normally with no errors at all. Right? We'll look at this more formally with POSIX errors in a moment. Right? But in any case, let's go ahead and come back to our demo here and capture that error code. Int error code is equal to AGM of that. And now I can make a decision. If the error code is equal to 1, right? Printf, oops, x cannot be 0. Right? And here, you know, it's more flexible and it's giving me more of the decision-making process here, but there's really nothing else I can do, right? If it's an error code of type 2, then I say, oops, y cannot be 0. Right? The only thing I'm doing here is giving a more descriptive message to the user, right? Else if error code is of type 3, printf, something went wrong with memory. Right? Debug, right? Else. Now, if there are no error conditions, I can go ahead and print out the actual result here. So let's try this again. I'll probably have to also change my prototype here to return an integer. There we go. That's saved. GCC my math. GCC everything together. Oops, I misspelled error code. Error code, error code, error code. There we go. A.out. Now, oops, y cannot be 0. If it's x, that's, or not 0, it cannot be negative. There we go. There. Oops, well, x cannot be negative. If I end up passing in null instead, it won't crash the program with the segmentation fault. Instead, it'll recover, come back to main, and say, oh, I didn't change x. Right. There we go, 42 and 42. It'll come back and say that something went wrong with memory. Right? But then I can continue as if I want to do other stuff down here. Right? This is way more flexible. Okay? And if everything else is fine, 42 and 101, and restore this result. There we go. The normal operations, right? It's 68 something. This is much more flexible because it gives you the decision-making process, right? It's not going to make the decision that we're just going to quit out of the program, or we're going to needlessly print stuff to the standard output that no human is sitting there watching, right? And nobody's looking at. And instead, we're going to give you the decision-making process that if an error occurs, you decide how to handle it, and that's called error handling. Right? So, why? Freeing up the return value means that you can do proper error handling in C. Error handling in Java is not more complicated, but it's just completely different. This is probably going to be one of the first things that that are vastly different in both languages. In Java, you have exception handling instead. But that's the topic of the next part here that we'll start here shortly. I just want to draw your attention here to, if I didn't have all this English here telling you what each one of these error codes were, fast forward 3 months, come back and just look at AGM here. In fact, just look at the header file here. Input values must be positive. It's not defined for negative values. Returns an error code in the event of an error. A tautology there, right? Just looking at this one function, are you going to remember? Oh yeah, 1 was if x was negative. 2 was if y was negative. 3 was what again? Right? Maybe there's more. 4 was something. 5 was something. Right? Are you going to remember that 3 months from now? Nope. These again are magic numbers. 1, 2, 3. Right? There's nothing special about them. I could have done 10, 20, and 42. Right? They're all true as well. Right? Are you going to remember that you were just went in sequence that day because you couldn't be bothered to think of weird numbers, or maybe I was just bored that day, so I used all these random numbers from a random number generator or something? You're not going to remember any of that. Right? It would be much better if you could have a human readable error code here. For example, negative x error, right? Something like that. Ooh, do we know how to do that? A human readable placeholder for some mysterious value. Some mysterious value like, say, 1.609. Do you remember what that number was? No? It's the number of kilometers in a mile, right? KMS per mile. How did we end up doing that? Using a define that thing to be that thing. And now I don't have to remember this mysterious 1 or 42 or 20 or whatever, right? I have a human readable error code here that I can use. That's one way of doing it. I'm going to show you another way of doing it instead, right? Just because we want to introduce more things here. Questions so far? I'm not going to do any of that in Java because, again, does Java have pointers? Nope. Instead, if you want to do error handling in Java, you're shopping for exceptions instead. Let's see, mark that. Just a second. So this gets into error handling. Errors in a computer can be completely unexpected or anticipated, but not normal. There are some errors that you cannot, you can kind of anticipate that they would happen. If somebody kicks out the plug on the server, can you write software to reach out of a dead computer and plug it back in? No. You can design stuff to recover from that, right? If the power completely went out in this building, we would be fine. Why? Because there are generators outside, right, that would kick on in the event of power loss. And so you can anticipate those kind of catastrophic errors, but in the software, you can't reach out and plug it back in. Some errors by nature are fatal. The program in general should die, right? Are very simple programs that we started out with. If you give me bad input, right, up front, or you don't give me enough input, right? I expect 3 command line arguments for, or what was it? 2 command line arguments or 3 command line arguments for your exam, right? If you don't give me those 3 command line arguments, there's not much I can do, right? So kill the program, right? Some errors you can recover from, right? You can anticipate them and not perform a dangerous operation, instead move on in some way. For example, a bad password. If you write a program that prompts a user for a password for security reasons, right? Nope, bad password. What do? Ask again, right? Okay, bad password again, right? Ask again. Bad password for the 3rd time. Now what should we do? Suspend their account, right? So maybe somebody's trying to break in or something, right? Apple phones did this, didn't they? That you put in the wrong biometrics or something like that, and then it waits 2 seconds. You do that wrong again, and then it waits 4 seconds or something like this. I don't have an Apple phone, so and you know it's security measures to make sure that nobody's breaking into it. Another nice security measure is a fail-safe, dead man switch, basically, where you know you've been captured. Give us your password. Oh, my password is 1234. Ah, excellent. You go and enter that password, and that is a password, but that password triggered a wipe the hard drive function, right? And so yes, you gave up your password, and now there's no way to get that data because the dead man switch has been triggered. It's actually better not to zero everything out. It's better if you actually re-encrypt it with a key and then throw away the key immediately, and then nobody can ever decrypt it once you've lost your key. Right? You have to. There's no way to recover from that, at least within our lifetimes. But anyway, you can decide how to handle those errors, and that's what's known as error handling, right? You can decide what to do in the event of an error, but you can only decide to do something in the event of an error if you know that an error occurred and if you know what type of error occurred. Let me go ahead and, oops, I might not, can I split left? Hopefully, there we go. All right, this is known as error handling. So again, the 2 languages are vastly different in how they do their error handling. In C, all right, in C, you use C, or C uses what is called defensive programming. Right? You look before you leap. And I never graded, I graded about like half of the midterms in the other section, but I didn't grade any in this section, so I don't know if this was an issue in this section. But one common thing that we saw was, I'll go ahead and grab the command line arguments, and then I'll check to see if there were enough command line arguments. Does that sound right? No, if there weren't enough command line arguments, how can I grab them to begin with, right? You do your error checking first. Are there enough command line arguments? 3 of them. If so, okay, we're good to go. If not, don't do that dangerous thing. You look before you leap, right? I'm about to take my next step. Am I about to step off a cliff? Right? What do? Do you step off the cliff, fall, and go, oh, oops, I guess I was wrong, right? No, you look. Right? That's defensive programming. You write code to detect potentially bad or dangerous operations before they occur. If so, you don't do them. Right? Instead, you if you are in a function, you return an error code that can be interpreted, and handled by the calling function. Right? Typically, you use an integer. 0 is some type of error. There. OBS was our stream lost 4%. Oh well. Non-zero is some type of error. Okay. You typically use a interpreted. It's misspelled. There we go. You typically use an integer because there's no such thing as an error of type 3.5, right? That's kind of weird. I mean, I guess you could, but there's no point in doing that. Errors are discrete things. Discrete as in ETE, discrete. Where there's 1, there's 2, there's 3, there's 4. It's not that's in contrast to continuous, like in calculus, right? You can infinitely divide things. That you treat all real numbers on the real number line. That's continuous, right? There's always another number in between. But with integers, with something that's discrete, there's not necessarily a number in between. They're countable, basically. Okay. And in Java, what do? In Java, Java uses exceptions. What are exceptions? Most modern programming languages use exceptions. Right? You try a dangerous operation. Right? You go ahead and leap. Right? Don't worry about falling off the cliff. If an error occurs, an exception is thrown. Right? And note here that I am using a different type there because throw is a keyword. We're going to throw an exception, which can then be catched. That's bad grammar, but I want to keep the actual keyword there. Catched and dealt with or handled. So go ahead and leap. Right? Go ahead and do your dangerous operation. If you fall, we will catch you. Right? And put you back up on the cliff and let you decide what to do. Right? If you want to quit at that point, go ahead. Right? You can kill the whole program. If you want to print an error message and send off an email, reprompt for that password, do whatever you're going to do, that's up to you. We'll catch you because you've fallen off the cliff. We'll put you back up on the cliff and let you go about your business, telling you what happened. Okay? And you've seen probably these keywords before in Java. If you have some Java background, try and catch and throw. Right? These are all the exceptions. Okay? All right, so we've already seen defensive programming in C. Right? In C, you design functions so that all the actual return values are communicated using pass-by-reference variables. Right? This frees up the return value so that you can use that as an error code, an integer that indicates the type of error. But here's a better solution. One solution, solutions. You can define error codes using the macro define, right? Define error type, and then 1, for example. I need some room here. There we go. All right. Or you can use what are called enumerated types. Right? So what's an enumerated type? Well, what's an enumeration? I used that word before without defining it. Hopefully it's just a regular common English. If I enumerate something, what am I doing? I'm listing them out, right? The first one, the second one, the third one, the fourth one. For example, the days of the week. What's the first day of the week? I'm asking because I don't know if there's going to be controversy or not. Monday? Sunday, okay, Sunday. Monday, anybody? Monday? Oh, okay, there's the controversy, right? You see, very, very seldom do you see those calendars that start on a Monday. And unfortunately, I can give you an example. Zybooks, when you set the due dates, their goddamn calendar starts on a Monday. So, and it's a 7-day week. So when I started setting things, I set things due on Mondays, thinking that I was setting them, but they all ended up being Tuesday because their calendar started on a Monday. I think that was a European that set that up, maybe. That seems like a very European thing to do. But in any case, no, the correct answer is Sunday. So what we're going to do is we're going to define an enumerated type. Why is this an enumerated type? Well, because there are only 7 days a week, right? There's the first one, the second one, the last one. right? Whatever we end up agreeing on. They aren't making any more, right? They're only 7 days of the week. They're not taking any of them away, hopefully. They're not adding any more anytime soon. So an enumerated type is an enumeration is a list of things, right? Example, days of the week, months, etc. And of course, error codes, right? So what I'm going to do in C is I'm going to define an enumerated type. In C, you can define an enumeration using the following syntax. And for this, I'm just going to go ahead and cut and paste it over here for the days of the week that start on Sunday. And then we'll come back on Friday to talk about this a little bit more. Walk through it really quickly here, though. Type def, all one word. What do you think that means? Type definition, right? Enum, well, what do you think that's short for? Enumeration, right? And then I have an opening curly bracket and a closing curly bracket. Within that, I provide the list of things. Sunday, comma, Monday, comma, Tuesday, comma, dot, 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 all the way down to Saturday. This is coding versions, code versions of the Oxford comma, right? It is optional. You don't have to put that last comma there. I like to put it there just to be consistent, because if you ever need to do come back and add an 8th day of the week or whatever, then the comma's already there for you to do it, right? You can choose to leave it off, or just like the Oxford comma, you can choose to leave it on or leave it off. It's up to you, right? As long as you're consistent about it. And then we have a closing curly bracket, and I name it day of week. And that's actually bad. I should have done it that way. I don't know why I did it that way last year. Weird. It should be upper camel cased, okay? So now I've got my own type, right? Just as I have an int, a double, a char in this language, now that I've put this up here, now I have a day of week type that can have the values Sunday, Monday, Tuesday, Wednesday, Thursday, etc., all the way through Saturday. There are some gotchas that we'll discuss on Friday, but there, really convenient, right? Now I can use human readable words, and we don't have a controversy about where it starts, right? Sunday is Sunday, Monday is Monday, right? And those are the key words that you use. And you can assign them, and then Tuesday comes after Monday, Sunday, et cetera, et cetera. Right? It is an enumerated type. I use upper camel casing here for the actual type name. That is a modern convention there that I'll encourage you to use. What did I do with each one of these elements, though? It's all uppercased. If they were multiple words, I would separate them by underscores, just like I did over here as a preview. Where is it? Oh, did I take it away? Yeah, there we go. Negative X error. All caps. Separated out by underscores here. Those are the conventions that we'll talk about on Friday. Any questions? No? Okay. Then I'll see you then.